Am I audible?
Yes, sir.
Okay. Good evening, all. So today actually I am using mobile network. So there may be a network issue. So during the solution, for that reason I will pause my video and then I will go for the solution so that the connectivity will be stable. Otherwise, the voice may be little bit breaking during the solution, so it will be difficult for you also. So good evening, all. So now let's move to the first question of today. This is the question number 14 of GATE 2014 Metallurgical Engineering. The question is, which one of the following NDT techniques cannot be used to detect an internal crack in a steel shaft? Option A, liquid penetration inspection. Option B, radiography. Option C, ultrasonic testing. And option D, X-ray tomography. Okay, so few of you have been answered it. Yes, option A, liquid penetration. Yes, this is correct answer. So, do you know how the liquid penetration technique works? Can you explain the steps? What are the different steps for the liquid penetration inspection? And which material you cannot use? Uh, in which material this technique you cannot use? This, even if there is a presence of surface crack, but toward the sample you cannot use this technique also. So let's go into the step by step. So anyone want to answer? What is the different steps involved in the liquid penetration? Cleaning the surface, dye on the material cooling for some time, and then there is one more step is there. Then you have to apply a developer. So okay, let's discuss the liquid penetration inspection first. So let's say this is a sample, and you have a external crack in the crack in the surface layer. So first you have to clean the top surface, and then you have to apply some dye or some penetrant. So this is a liquid. So it will, because of the capillary action, it will penetrate into the crack. Inside the crack, it will go inside the crack. Now we have to clean the dye again. So the top surface of the material, uh, from the top surface the dye will get cleaned, but in the internal crack, inside the crack, that dye will be there. Now we have to apply some developer, as you can see here. So when the developer is a kind of porous material. Okay, so what happens again, because of the capillary action, the liquid dye which was present inside the crack, this will again, because of the capillary action, it will go up and it will go to the developer, so that after some times on the developer will get, you can see colored region. So that color region will basically show the area where the crack is present. So everyone can see this screen, right? That what are the different steps involved there? Yes, now applying the developer, now you can see that from the crack, that dye will go upwards because of the capillary action, and it will make a mark on the top. If this is the crack, when we apply the dye here, no? So because of the capillary action, the dye will go up and it will create a mark here. So if you visualize in the three-dimensional thing, let's say this is your sample. There, there was an internal crack, surface crack is there inside. So now if you apply the developer on the top, let's say this is the blue color is the developer, and red color is the your penetrate, which is there. So if there is a multiple crack, after some times you will see there is one line, red spot. If there is also one internal subsurface crack is there, there will be line. So this location of this color region will show you the location of the crack. So in this technique you can identify the surface crack. But let's say if one crack is present inside, can you identify it by this technique? It will not possible, right? Because that penetrate or that dye cannot penetrate inside this internal crack. So for this you have to require some other technique. Okay, so uh, so everyone understood this part, right? How the liquid penetration inspection works. Any doubt regarding the different steps involved? Anyone? Okay. So can anyone tell me what are the limitation of this technique? For which cases you cannot use this? In which case you cannot use this technique? Even if you have surface crack, no, yeah, subsurface, okay. But let's say you have surface crack only, but still you cannot use this technique for some special kind of material. For which material? No, crack I'm not saying. Yes, yes, why? Yes, exactly. So if your sample has porosity, then this technique will not work because that inside the pores also that dye will go inside, right? So then at the location of the pores also that when you will apply the developer at the location of the pores also that colored dye will be visible. So in this technique you cannot distinguish which are the pores, which are the surface crack, right? So for those sample you cannot use for ceramic or for oxide sample. So oxide also have porosity. So for those kind of sample you cannot use this technique. Okay. So now what are the other technique are mentioned here? Radiography, ultrasonic testing, and X-ray tomography. So do you people know about the radiography? What is radiography technique? How is what data it will give? It can identify the surface crack or internal crack or both. Anyone? Subsurface crack means what is subsurface crack? Subsurface crack means let's say this is your sample, and if the crack is very near to the surface, but it is not a open crack which is exposed to the surface. This is the surface crack which is open to the surface, and subsurface crack is very near to the surface, but it is not open crack. So now if you apply the liquid here, that dye here, so what is the principle that dye penetrate? It penetrates because of the capillary action, right? So you have to have the open area here, or else how it can penetrate, or how it can go to that inside that crack. So it will not be able to go inside that crack, right? For subsurface crack, one technique is also there, uh, magnetic inspection. I think, have you heard about this magnetic? Okay, so in that case, what actually people do, let's say this is your sample, and let's say this is a subsurface crack. So if you apply a magnetic field on this sample, na, so what will happen? So every sample, if the limitation is that your sample has to be a magnetic sample. In the applied field, it should convert into a magnet. So in that case, that uh, dipole will be arranged in the north and south direction, right? NS, NS. Okay. So if your material is a continuous, no pores or no crack is there, then NS, NS, like this it will be arranged so that at the end you will get one side north and one side south. Yes, magnetic particle inspection. Right? Uh, so, but if you have pores or crack inside, you will get locally north-south pole here near the pole. So then what will happen if you put some magnetic particle or magnetic any kind of liquid or magnetic very particle also, then it will be aligned in this location where the local north south poles is created. That location it will get aligned, that magnetic particle will get aligned here. Even if it is a subsurface region, but there will be a little bit magnetic field over the that region also, because so it will, that particle will get aligned here. So, but if your track is very much deep inside, then the field may not be that much of height, so that it cannot give you the exact location of this internal track, but it can give you the location of the subsurface track or location of the surface track. So these two you can identify from the magnetic particle inspection. Okay, and using the radiography also you can identify surface track also, and also the subsurface or internal track also. So can anyone tell me what is the principle of the radio particle inspection, radiography, sorry, radiography inspection? That schematic is visible in the screen. You can, yes. Then what is the principle? Yes, we use X-ray or gamma ray, send on to material. Then how you will get the contrast? To observe. So you can see. So this is a material. Okay, and this is the film or detector, anything. And this is your material. Somewhere it is thin, somewhere it is a bit thick. Okay, and one crack is inside, internal crack is there, you can see. Okay, so now what happens when you, if you use the parallel X-ray source or gamma ray source, any radiographic source, what will happen? Let's say I am drawing this image here. Let's say this is a crack. Now your one X-ray is coming from this, one ray is coming from this location. Let's say like this, your X-ray is coming. Now if you place a film here, what will happen? In this region your X-ray will be absorbed more, right? Because it is traveling through the sample, so it is getting more material and is crossing the more material, and then it is penetrating here. Now in this film, if the more intense X-ray will come, but it will make that location more black. Okay, if the less intense beam is coming, then it will not cause that much of blackening of that film, right? So now let's consider this location. Here one crack is present. Crack means there is no material is there. So in this ray will absorb less because it is not getting the whole material. As here it is getting the whole material, but here it is traveling only through this portion of the material, and because of the presence of an internal crack inside. So the intensity of this ray, let's say intensity of this ray is I1, intensity of this ray is I2. So intensity of I1 is less than intensity of I2. Are you getting? So what it will cause? It will cause much more. It will cause less blackening of the film, and this ray will cause more blackening of that of your film. Anyone of you have seen that X-ray report? In the medical purpose also they use, right, for identify the fracture in the bone. So it is almost you can say it is almost a similar kind of thing, but here only projection actually basically they take in radiography inspection. So 2D projection only they take. Okay, but X-ray tomography, that also I will explain later. X-ray tomography, there you will get a 3D image of that thing. They are actually, they rotate the sample in three-dimensional space so that and then I construct a three-dimensional image of your sample. But here you are taking a projection of this. So at the location of your crack, it will cause much more blackening of the film. As you can see, here the thickness of the sample is less. So that's why here no sample is there. So it is totally black. Here the thickness is less. It is a comparatively lesser black, but it is a dark region. Now the thickness is getting higher here. That's why the contrast also is changed. It is going in the grayish region, right? Now in this region you have to track when your X-ray or gamma ray is crossing through this sample, this portion, you can see the projection of that crack here on the screen. So this way you can identify the presence of any internal crack. Even if there is a surface crack or also a subsurface crack also, that also can be find out, because it is work on the principle of the absorption of the X-ray or gamma ray by the material, right? So due to less observability, yes, defects are darker because absorption will be less at that region. Whenever your X-ray will pass through any sample, let's say this is a X-ray source, so your X-ray is passing through any sample, so this sample itself will absorb some portion of your X-ray, right? But whenever there is a crack or hole, at that portion X-ray will absorb less. So that means intensity will be more. Are you getting my point? Yes. Okay. So that portion, your intensity of the X-ray will more. Now you know that photographic film, right? But if you pass the X-ray through this film, it will cause that film it will turn that film in black, right? Now if there is no sample, you are passing only X-ray, then that film will be totally black. It will be a dark black kind of thing. As you can see here, there is, if you draw a line in this region, there is no sample is there, so that film become totally black. And this area thickness is less, that's why it is not totally black, but it is a comparatively much blacker than the contrast you can see. This is a lighter and this is a darker, right? And, and because of the same reason, when there is a crack is present at that area, intensity of the X-ray will be, or X-ray or gamma ray will be high. So it will cause blackening of that location, particularly that location. So in that case, you can see a contrast where your crack will be present. If you have multiple cracks, let's say this is your sample, one crack is there, one crack is there. Now if you take the if you do the radiographic inspection, then you will find in this field, you will find one black region here, one black region here. So depending on the location of your crack. So this process is helpful to identify the internal crack. So clear this one? Okay, okay. Then I'm moving to the next option, that is ultrasonic inspection. Anyone can tell me what is the principle of ultrasonic inspection? Virendra, Vikas, Manas, any one of you can answer. What is the principle? If you don't know, also you can try. Like, okay, I'm playing this video. You can see, and then you can try to answer. Just observe this carefully. Is it feasible, right? Yes. So one video was played. Then now I'm playing the next video. Now it is doing the reflecting from the crack. Now we will get one extra hit because of the crack. Can anyone explain how this is happening or why? Okay, okay. So let me explain. So in this case, one probe which is connected with a transmitter and a receiver. So it transmits a sound wave and it also receives that reflected sound wave. Okay. So now when in your sample there is no crack, let's say this is your sample. So now and this is the transmitter. So you are sending sound wave. It will go travel through the sample. When it will find a free path, it will again reflect back from this location from the free surface. Again this wave will reflect back to the probe. Uh, so it will receive back that signal again. So now let's say your sample has a defect inside. So as you can see in the first video, uh, so in this first video that transmitter is sending signal at this location where no defect is there. So first peak is the because of the sending of the signal. This is the intensity of the sound and this is the time. In the x-axis it is time. So first peak is because of the intensity of the transmitted signal. Now it travels to the sample and then it reflected back again at the receiver. So this is called backwall echo. When it reaches that free surface, it again reflected back to the receiver. So because of that, after some time, you will get one more peak. This is because of the reflected wave from the free surface. And also you can see there is intensity difference. Can anyone tell me why this intensity difference is there? It is not encountering any defects or anything, but still there is a intensity difference is there. Why? Yes. So when the sound is traveling through that your sample, some part of it get absorbed also. So because of that, the intensity is a bit less in that location. Okay. So now let's. So what we do? So in this technique, this transmitter or this probe is scanned throughout the sample. So this, let's say this is the first location of the probe. Now we will move the location of the probe in this location. So now what will happen? Your sound will travel through this location. It will encounter one defect, and then it will reflect back again. So in this case, what will happen? In the first case, that wave is traveling more distance. But in the second case, your wave is traveling a less distance and then it is getting reflected. So how will be your graph? That intensity versus time. Let's writing I. So let's intensity versus time. So one peak you will get because of the transmitted, and another peak also you will get because of the reflection of the sound wave. So at which location you will get that peak? Will it be at the same location here? Will it be here or will it be in this side? Which side it will be? Let's say this is 1, 2, 3. At which location it will be? The peak. Anyone? 3. Why? Why 3? The x-axis there is time and the y-axis will be intensity. Obviously intensity will be less. Okay, time will take time taken will be more. Why time? More time will take. Why? Okay, plus one. Now you have answered 1. Why? Okay. Okay, because are you getting it? Why it will take less time? Yes, Prasanna is right. It will take less time because you can see that distance is more in the first case. This is a this much of distance. But when it is encountering a defect inside, it is taking a it is traveling in less distance, right? So that's why in this case distance is less means time will be taken less, right? Your velocity of the sound is same. It is not getting changed. Velocity is same. Velocity through a medium will be same. So if the velocity is same but distance is decreasing, that means time taken will be less. So in this case, you will get a reflected peak here at this location, the location 1. It's at the left side of the initial location. So now, from this time, how much time it took to get back from that location. So that means, let's say time it take t time, okay, and let's say this distance of the defect from your surface is x. So that means that your wave is traveling how much distance? It is going x inward and again come back x distance outward. So it is basically traveling 2x distance. 2x distance it is traveling, okay, and it is let's say the velocity of the sound in this medium. Let's say if it is v of s, then you can easily calculate the time, okay. Now time you will get you can note from that probe. So you know the time value, you know the velocity of sound of in this medium. So now you can calculate the x. So that means you will get the location of the defects where it is present, at which depth the defect is present, that you can find out. Similarly, in the second video, you can see some part of the wave is deflecting through the crack and some part is deflecting from the from the surface. So that's why you are getting one echo here or one pulse here. Then when some part is deflecting from here, this is going back. So this reaches fast. That's why you get one echo here. This is because of the defect. Okay, and the end, this is again from the surface. Okay, so in this case we will get total three echo or total three peak you will get, because some part is deflecting from the defect and some part from the free surface of the sample. And how much time it is taking, this time you can measure from this graph, okay. And if you know the velocity of sound in this medium, then you can easily calculate at which location your crack or your defect is present. So this is ultrasonic inspection. So everyone is clear with this? Because you understood?
Yes, sir.
Okay. So now this is the last option of that question. X-ray tomography inspection. It is that principle is almost similar to the radiographic inspection. Here also uh, act on that principle that your X-ray will get absorbed by your sample. But here what people do, so this there is a stage is there and this is your sample, which is placed on a stage which can rotate or which can be tilted, which can rotate like this or which can be tilted also. So that means it can scan your sample in the three-dimensional space. So there is a source of X-ray is going through this. Collimator means here actually your source will be parallel. It helps to make your X-ray source parallel. So your parallel X-ray source is going there. Now it is let's say from this rotation or 0 degree rotation you click one image. So it is it went to the detector and then you rotated your sample up to for a few degrees, let's say 15 degrees you rotated your sample, and then again you took that image, and then basically your computer will reconstruct all these images and it will give a 3D model of your sample, 3D print of your sample. Let's say if your sample is like this, so now you cannot see what is the crack or what are the pores present inside. But if you place your sample here in this X-ray tomography inspection machine and you rotate your sample at different angle and reconstruct the image of the of your sample in X-ray tomography unit, then it will show the location of the internal crack, location of the pore. It will give you a 3D image of your sample. So a 3D image you will get. Okay. So now that 3D image also you can rotate and you can see from the different direction, and you can basically understand that exactly at which location your crack is present and what type of the crack is there. If you just see a 2D projection, let's say this is your shape of your crack. Now if you take a 2D projection, what will be the crack length? This much, right? So this will be your length, but your actual length is this. In the projected image, the length will not be exact. Okay, let's say this is your orientation of the crack, and you are taking the projection from this. It will be look like a point here. So it will look like a point here, right? So you will not get exact shape or exact size of the crack from the 2D projection. So that's why in the X-ray tomography inspection you can get a 3D image, so that you can rotate from the different direction and you can see from the different orientation, and then you can clearly understand what is the exact shape of the shape of the crack or porosity, and what is the exact size of those porosity or those crack. That you can easily understand using this technique. The principle is same. The principle is same as the radiograph. So everyone understood? It is like people are using this technique from long ago. Like, not very advanced technique. It is not a very advanced technique, but it is means in practice right now. In NDT, people use this technique. Okay, so we solve this first question. So now you know all the technique, the principle of all the technique, liquid penetration, radiography, ultrasonic testing, X-ray tomography, right? So using all the technique, you can uh, you can see the location of the surface crack or subsurface crack, but you cannot detect the internal crack using the liquid penetration. So your answer is option A. It will be only helpful to detect the surface crack. But all the other technique, it can detect the subsurface crack or internal crack also. Okay. So correct answer is option A. So now let's move into the next question. Okay. So this is the question number 45 of GATE 2014 Metallurgical Engineering. The question states that consider a steady state heat flux across a rectangular slab composed of two layers of equal width as shown in the figure below. The thermal conductivities are in the ratio of K2 by K1 is equal to 10. If the first layer experiences a temperature drop T1 minus T2 of 50 Kelvin, what is the temperature drop T2 minus T3 in the Kelvin across the second layer? So this T1 minus T2, this is given, this is 50 Kelvin, and the ratio of this K2 and K1 is also given. So K2 by K1 is given, this is 10, and T2 minus T1 is given, that is 50 Kelvin. So what you have to find out? What is the temperature drop? That means this side, that is difference between this T2 and T3 in Kelvin. Just concentrate on the few terms. One is steady state heat flux. This is an important term. Okay, and equal width as shown in the figure. Okay, the same 500. Okay, I will calculate and then I will see. We will see it is 500 or else. But can you just tell us how you approach this question, how you have calculated? If you just concentrate these two important term in the question, you can easily solve this. Okay. Okay. So now just I will just give some hints first. So it is a steady state heat flux means what? It is not accumulating, right? Steady state means it is whatever heat is going inside, that much of heat is coming outside. Okay. Is it coming 500? Are you sure? Okay, let us calculate and then we'll see. Okay. So first let me explain the problem here. So it is mentioned is steady state. Okay, steady state means if Q amount of heat is going inside, Q amount of heat will go outside. Okay, there will not be any accumulation of the heat inside. If the heat is getting accumulated inside, what will happen? Let's say if you consider this interface, if your heat is getting accumulated, what will happen? The temperature this interface will rise and it will be somewhere like this. But as it is not accumulating, so your heat as much heat is going inside, that much of heat will come outside. Now let us break this slab into two pieces just for the sake of solving this question. So let's say this is the T1 and T2 and this is T2, T3. If Q amount of heat is going from there, this wall, Q amount of heat will come out from this wall, and also Q amount of heat will come out, go through this wall and will come out through this wall. Now what is the flux? Q is minus A into d T by dx, right? Flux. This is heat flux. Sorry, heat per unit area. Heat flux. So this is the area. Area is also same for the two slabs. So that means your amount of heat will be K into A minus K into A dt by dx. So for this slab it is K1. For this slab it is K conductivity is, for this slab it is K1. For this slab it is K2. So now if you write the Q for two different slabs, you can see that Q is equal to, for slab 1 it will be minus K1, area is same, so it will be A into dt means how much? T2 minus T1, right? For this one, T2 minus T1 by x, that is the distance or width of the slab. Let's say both are x because it is mentioned equal width, so by x. Okay, for this one is Q, and for this two, let's say and timing is Q1, or both will be same, so it will be Q only. So which will be equal to this Q also, because it is a steady state. So this Q also will be same. What will be this Q value? It will be minus K2 into A. What is the temperature difference? T3 minus T2 divided by x. Okay. Now x will cancel out, A and A will cancel out. Now you need to know T3 minus T2, right? T3 minus T2 will be how much? K1 by K2 into T2 minus T1. So what is the K1 by K2? K2 by K1 is 10. So K1 by K2 will be 0.1, right? So 0.1 into 50. So how much it will come? 5. It will not come 500. You have to check carefully. It is ratio K2 by K1 is given, not K1 by K2. So this simple mistake sometimes many people do, and because of this simple mistake, even you know the problem, you will just lose your marks. So you have to be very careful when you are solving this question. Everyone understood? Your formula is correct. Okay, T1 minus T2. B means heat. Okay, K1A. No, K1 will be in the top, right? Formula will be this. Q will be K1A T1 minus T2 divided by D. This will be the formula, and this will be equal to K2A T2 T2 minus T3 by D. Because heat flux is given by heat flux is proportional to dt by dx, temperature difference, that is the driving force. Driving force here is temperature difference, and the distance is dx. So q is this heat flux. So it will be minus k dt dx. Dt, because the minus sign is because it is flowing from the higher temperature to lower temperature. Means down the concentration gradient, not on the, down the temperature gradient. That means temperature is decreasing. That's why it is termed as a minus. Okay, that's why it is minus k. And this is flux. This is heat flux. If you write total heat, then it will be minus k into a. You have to multiply it by area, then dt by dx. Okay. This for steady state, this total q or heat flux will be same. So there will be no heat accumulation at the interface. So this will be the formula. So you know K1 by K2 ratio, A and A will cancel out, B and B will cancel out, because area also same and the thickness will also same. So just simply, if you do the ratio, then you will simply can calculate T2 minus T3. So in this case, the answer will be 5 Kelvin, not 500. Everyone clear? Everyone understood? Any doubt? Anyone has any doubt? Others, are you following? Devendra, Manas, okay, it's clear, right? Okay, so okay, I just want to give a simple analogy of this to solve this problem. So it will be some bit easier also. Like, in this case, it was the slab are connected in a series. Just two slab are like this. Okay, so you can simply use the resistance, current and resistance analogy. So let's say this is resistance 1 and this is resistance 2. This is your Q1, this is Q2, this is Q3. In this case, in case of current, what happens? Q1, Q2, Q3. So current is, what is the formula for the current? Q equal to IR, resistance, right? So I means, in this case, your I means Q. What is flowing? Q is flowing. So I means Q. And V means temperature. Because in case of current, what is the driving force? That voltage difference across the two resistance, right? This is the driving force. In case of heat transfer, the driving force is the temperature difference. So V is analogous to T and I is analogous to Q and resistance is analogous to that we can find out from this formula. Okay. So you know Q is minus K dt by dx. Now if you write in this kind of form, that is dt will be for q by minus k by dx. Am I right? If you write in terms of heat flux, then it will be this. If you write in the total heat, because total heat is flowing, so it will be Ka. Ka. Total heat. Okay. So that means now you can see our equation is analogous to this form. In this case, V is analogous to T, delta T, or the temperature difference. This is V is equal to IR. I means Q value. Q into R means R means 1 by Ka by dx, or your distance U. So what is R? R is x by Ka, or dx by Ka minus of. So this is R. So now in this case, as the slab are connected in series, so similarly you can use the analogy of this series analogy, and you can find the total Q. What will be the total Q? Total Q will be simply the Q will be, so V equal to IR, right? So I will be V by R. So what is V here? V is temperature, T1, T3. So total Q will be simply T3 minus T1 divided by total R. R will be R1 plus R2. R1 is x by K1 A, and R2 is x by K2 A. Okay. If you put this R1 and R2, you will simply get the total Q from this. Okay. Now, for this simple question, this if you solve like this also, how I have solved in the earlier, so this will be also fine. But let's say sometimes the question come like this. This is one slab. Now this is another slab. This is another slab, and this is another slab. The total 4 slab is there. In this case, if you try to solve like this, which approach I have solved earlier, this will be a bit complicated, right? Now, if you just simply converted it into a this current analogy, it is in series. Okay. Now, from this interface, you have 2 different paths. That means these are in parallel. Again, one series. In this case, what will be the Q? Q will be this one R1, R2, R3, R4. So what will be the effective resistance? R effective, what will be the effective resistance? First will be R1 plus this will be how much? R2, R3 by R1 plus R2, because they are connected in parallel, and then plus R1. So, R4. So you got the total resistance for this circuit or for this slab orientation. And then if you know the R effective, then the Q effective or total Q will get simply just temperature from this side, let's say Ti and T, let's say To and Ti. Ti minus To divided by the R effective. In this way, it will be a very much simple question. You can easily calculate the Q effective, or else you will find difficulty to calculate for each part, and then you have to add up Q value for this one, Q value for this one, what is the Q and this location. It will be a complicated situation, but if you simply convert it into a current analogy, this analogy, then it will be a bit easier. Have you understood this one? Okay. So should I move to the next question? Anyone has any doubt? I think this kind of question people have solved earlier also in class 12 also. This kind of problem was there. I think it will be easy for everyone to understand, right? If anyone has any doubt, you can ask me now. Okay. Okay, then okay, now let's move to the next question. So this is the question number 37 of GATE 2014 Metallurgical Engineering. Assume that Sievert's law holds for solubility of hydrogen dissolved in the thin metal foil. If the partial pressure of the hydrogen in contact with the foil is increased by a factor of 2, the solubility increased by a factor of. Okay, so anyone want to approach how to solve this? What is Sievert's law? Anyone? If you can unmute and answer. This is a very easy question. Okay. 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 Even if you don't know the Sievert's law, you can be able to solve this question if you read the question properly. So assume that no one of you don't know Sievert's law. Okay. So now ignore this part for the time being. So now, what the question states? It states the solubility of hydrogen dissolved in a thin metal foil. So now hydrogen is a gas and it is a diatomic gas. So initially you have hydrogen gas in the gas form. Okay. Now what it told? It is told that that hydrogen is getting dissolved in a thin metal foil. So that means this hydrogen gas is getting dissolved in the metallic film. Means how it will dissolve? It cannot stay in the gaseous form inside the metal, right? So it has to go in the atomic level. Then only it can dissolve on a metal. Let's say this is your metal. Okay. Now it is in a hydrogen atmosphere. So now how this hydrogen will get dissolved inside this metal? In the H2 form it cannot dissolve, right? It has to break in the atomic form. Okay, first it will break in the atomic form. So first it will break in the atomic form and then it will get absorbed on the surface. Okay, so the surface is absorbed, then it will start diffusing inwards depending on the temperature and time and the rate constant of the reaction. Okay, so when it reaches the equilibrium at that time, that will give you the maximum solubility for this for the certain condition, for the certain temperature and pressure. So let's say at a constant temperature and pressure, because if you vary the temperature and pressure, and this solubility will change depending on the temperature. The diffusivity of this atomic hydrogen will also vary, and also it will also depend on the pressure. So that means from the gaseous form it is going in the atomic form. It is dissolving means it is in the atomic form. So hydrogen in the atomic form in the metal. So this is nothing but a chemical reaction. You can consider is a chemical reaction. Okay. Now I think every one of you know the rate constant, or how k of this chemical reaction you can write. It will be the activity of the product by activity of the gas, right? So up to this you can write even if you don't know the Sievert's law. Everyone, right? Yes. So now, what is the activity of a gaseous, uh, any gaseous form? It is nothing but the partial pressure of that oxide of that gas, right? Activity of any gas is given by the partial pressure of that gas, and activity of means dissolved hydrogen in the metal. Let's say at a constant temperature and pressure, it will be constant, right? It will not. Sorry. In the equation, I did one mistake. So I also have to do the mole balance, right? So 2 mole of hydrogen was there. So it will be H2, if it is H2, it will be 2H, right? I have to do the mole balance. So it will be activity of hydrogen whole to the power whole square. So activity of hydrogen, this will be simply proportional to the mole fraction, or you can write it as amount of the dissolved hydrogen. Okay, it will be proportional to the mole fraction or amount of the dissolved hydrogen. If the amount of the dissolved hydrogen is increasing, your activity will also increase. It mostly follows the Henry's law. Dilute. It will be partial pressure of hydrogen. This K is constant at a constant temperature and pressure, right? For a reaction, the K is constant for a constant temperature and pressure. Now, if you write dissolved hydrogen concentration in terms of partial pressure of hydrogen and the active K value, it will be K into K to the power half into P of hydrogen to the power half. If you replace this constant with other constant, that is K prime, K to the power half PH2 to the power half. So this is the equation. That means amount of dissolved hydrogen at constant temperature and pressure is proportional to partial pressure of hydrogen whole to the power half, or root over of partial pressure of hydrogen. So this is the equation, or this is basically this is the Sievert's law. Now you can see, if you don't know the Sievert's law also, then you can also derive, just reading the question you can get to up to this point what is the Sievert's law. You can also derive the equation, right? So we have to read the question carefully, then that is the reason. So but now I will tell what is Sievert's law. Sievert's law basically states that at constant temperature and pressure, the visual concentration of any diatomic gas, it need not to be hydrogen only, it may be hydrogen, it may be oxygen, it may be nitrogen. At any diatomic gases, visual concentration of any diatomic gas will be proportional to the partial pressure of that gas whole to the power half, or root over of partial pressure of that gas. It may be oxygen, or it may be hydrogen, or it may be nitrogen. For any gas, the dissolved concentration of that gas will be, of that diatomic gas, will be proportional to the partial pressure of that gas whole to the power half, right? So now, even if you don't know the Sievert's law, you can get up to this point, right? Now we got that equation. Now this question becomes much more simpler. Okay, so I have to add one more slide. Okay, now we got this equation. The dissolved concentration of hydrogen is proportional to root over of partial pressure of hydrogen, right? Now the others value are given to us. So what the question states, the partial pressure of the hydrogen in contact with the foil is increased by a factor of 2. That means if initially partial pressure of hydrogen is pH to 1, and later it becomes partial pressure of hydrogen 2, then that means pH 2 by pH to 1 will be factor of 4. That means 4 times, right? So this increased by 4 times, and the question asks is the solubility increased by a factor of. That means if initially your solubility of hydrogen was H1 and then later it becomes this one. Then you have to find the ratio of this. Right? So now if you simply write the equation from the Sievert's law, this is H1 root over of or is equal to K. This is the constant K partial pressure of hydrogen 1 and H2 will be K. This constant will be same for a constant temperature and pressure. So this K will not get changed. K will be same. If you take the ratio of this equation 2 by equation 1, then you will get the power of this is how much? The power of 4. That means 2. So everyone got this one? Anyone has any doubt? Understood? Now you know the Sievert's law also, right? What is Sievert's law? Can you will type in the chat box what is Sievert's law? Anyone? Or you can unmute them. No, concentration is not directly proportional to the partial pressure. Even here also the equation is given. Seeing this equation you can see it is not directly proportional. First thing you have to mention at constant temperature and pressure. It is very much important. Yes, it's quite. So also you have to mention the constant temperature and pressure because it is also very much important. Because if you change the temperature and pressure, then also your solubility will vary. Okay. So remember two important terms. One is constant temperature and constant pressure. These two terms also important. And again, this term is also important. The diatomic gas for diatomic gas only. It will not be a square root. It will not be proportional to square root if the gas is not diatomic. Okay. Then it will not proportional to square root of. Then it will be something else. Let's say if your one gas is B and it is not B2, it is Bn. In this case, what will happen? It will be equation will be N into B. In this case, your K will be dissolved concentration of B holding per N and then partial pressure of Bn. In this case, your dissolved concentration of B will not be square root. It will be partial pressure of B N holding per 1 by N. When it is N is 2, that means for diatomic, then it will be square root of B, right? So it is important that you have to mention for the diatomic gas and you also have to mention that constant temperature and pressure. Then only your dissolved concentration of that element will be directly proportional to the square root of the partial pressure of that gas. Okay, understood?
Yes, sir.
Okay then. So everyone is okay with all the questions that are solved today. All the concepts are clear. Questions was very easy, so you can solve easily. No doubt that. But I want to ensure that every one of you are clear with all the concepts that are covered today. Right? Everyone is okay. This was the first question. Second question was the heat flux, and the third question was based on the Sievert's law. Okay. Okay. It seems everyone is clear then. Okay, then we'll meet in the next Friday again. And if you people have any suggestion or anything, you can share with me also. Like in which way if I solve the question that will helpful. Anyone has any suggestion or anything? Okay, if not, then we'll close the session for today. We'll meet again on the next Friday.